Good. So today I'm studying from home. I'm not going to college. I'm not going to class today. And I'm gonna skip conjugate gradients and I'm gonna come back to it in after I finish all of this. And I want to move forward now. I want to study interpolation. So consider a function in a function space. Let now find on basis of the n-dimensional space. The task that we are interested in finding is a function v star that approximates with coefficients equal to Cn. If we have an inner product, the best approximation of f in Vn with respect to the induced norm is given by the projection where pi n is the orthogonal projection of onto Vn. Right. If we are given an inner product, we can just project our function f star onto the basis of the f and combine them in their coefficients. However, in many cases we cannot directly compute the projection of f onto Vn because we have too little knowledge about f. But what is interpolation? Consider n pairs of data samples. You now want to find an approximation that is close to f. For example, we could enforce the interpolation condition. Also use regression and minimize. The error of f tilde with respect to f can then typically be split into two components. Where f one page of information. Okay, one page at a time then. Where f tilde is equals to this, right? The projection of f onto, no, that's f star. What's f tilde then? Okay, so f tilde is okay. F star is the projection of function on the space, and f tilde is interpolation such that f tilde xi is equals to f of xi. That's all we know about the function, right? That's why. So f tilde error can be split into two components. Right. So if I have the function f, then f tilde minus f, that error in the norm, whatever norm this is, function norm, is less than or equal to lambda. This is some constant, and this s star minus f, where s star was this. So this means like f star is the best approximation of f in this space, whatever space we are in. So the projection error describes the best we can do in the space Vn. Even if we had full knowledge of f, we could only compute this. We are limited by the expressiveness of the space Vn. That is correct. Intuitively, we'd also expect the error of f tilde to depend on the points x1 to xn at which we have samples of f. This captured by the constant this, that is independent of f but depends on x1 to xn. So this only depends on the points. It's split into two parts in errors. This one only depends on points and this one only depends on the space, the function, the whatever we are projecting on. So polynomial interpolation. Consider n plus 1 pairs Consider n plus 1 pairs x1, xi, yi, and okay. So consider n plus 1 pairs xi, yi of function f with yi equals to f of xi, and we want to interpolate using a polynomial. So Pn, this is like the space, this is like the function where we are projecting our own main function to. Pn with a set of all polynomials up to degree n over r. So that we have for all p belonging to Pn, we have this relation a0 plus a1x plus a2x square plus a3x cube, etc. We would like to find p belonging to Pn such that p of xi equals to yi. We would want to find yes, so that's what we are doing, right? We are going to enforce this condition by making our p of xi equals to yi. This is what f tilde was on previous slide. Yeah, exactly. By saying polynomial of degree n, we split vn plus 1 with the notation. Yeah, we have fixed a space. Given n plus 1 points, there exists a unique polynomial such that so n plus 1 points is a unique polynomial of degree n. Yeah, it's good to know. We sometimes refer to this unique polynomial as pf. Instead of proving this theorem, let's try to construct the polynomial. What do we need to construct the polynomial? We need a basis. Right? Let's give the monomial basis a chance. So this is known as the Van der Waals matrix. We are going to solve the Van der Waals matrix A equals to y. Condition number of Van der Waals matrix is very high, and that's why we don't use Van der Waals basis. We don't use monomial basis because the condition number is very high. Let's look for another basis. The Lagrange basis. Where was Lagrange from? This was a French guy. Definitely his name is Joseph Louis. Oh, Euler. Oh, his academic advisor was Euler. Do you know Euler was Swiss? Nice. Who's Bernoulli? Jacob and Johann and Jacob Bernoulli. Who's Eglinger? Never mind. So Lagrange polynomials are uniquely defined for distinct x0 to xn. They are defined Li xj is delta ij. So it's like they are one at the point in which they are supposed to be one. So for example, let me write it at let me see if I have points at x0, x1, x2 and x3. all right, these are the points I have. So Lagrange polynomial, the L0 polynomial, is supposed to be L0 x0 is 1, L0 x1 is 0, and so forth. So it's definitely x minus x1, x minus x2, x minus x3, and at x0 this has to be 1, right? So x0 minus x1, x0 minus x2, x0 minus x3, then it is 1, and there are 0 all the way other than x0. And x equals to x0, it's 1. Okay, this is correct. So yeah, let me just, I know how it is written. Li, the ith Lagrange polynomial is xi minus xj product for all j not equal to I, and here it's x minus xj for j not equal to I, right? Yeah, perfect. So what are the coefficients for this Lagrange polynomial? The coefficients are just the function values, right? Right. P of x is yi li of x. Because at xi this is 1 and all other xi's is 0, so it's yi. That's correct. P of xj is yj. Cool. So if we have the basis, if we have this basis, all we have to do is just plug the values of x, y, and we have the polynomial. So basically all there is like is calculate this basis, and you just have to put yi's, and that's it, you're done. You have the polynomial, you have the interpolating polynomial accurately. Right? What's the problem with this? Cost of evaluating the polynomial for any other point. Let's say if I want to evaluate the polynomial at point here, midway somewhere, so I have to calculate this, all of the Lagrange polynomials at that point, which may be not too easy to do, right? You have to multiply a lot of things, divide a lot of things. not divide, multiply. The Lagrange polynomial are orthogonal with respect to the inner product. Let's try to generalize. So over this inner product, the Lagrange polynomials are orthogonal. Yeah, because they are only they're like zero everywhere else except their own point, and any two Lagrange polynomials are just orthogonal with respect to this inner product. Let's try to define inner product with respect to functions now. Like we said that if we can define with respect to a function inner product and then find basis of a function space, all you need to do is just project f star onto that function space and you're done, and you can project by using inner products. So inner product between two functions f g is an integral over a and b omega x f of x g of x, where omega x is like a weight function. This is like the xy inner product with a was x transpose ay, right? That's how it's, this is the same. This is the w weighted inner product, omega weighted inner product. Let p1, p0, p2, pk be polynomials respectively of order up to order k. They are called orthogonal polynomials on a to b with respect to the weight function if it holds. Yeah, they're orthogonal. So if it's like if pi pj is delta ij, and when they are equal, they are the norm of pi square, and norm is defined as per here square root of the function. Okay. To define orthogonal polynomials uniquely, we require the leading coefficient to be 1. That is, yeah, the leading coefficient is 1. Pk of x is xk. Okay. There exist uniquely determined orthogonal polynomials with leading coefficient 1. These polynomials satisfy the three-term relation. The fuck is this, bro? What is the inner product? We are gonna that's what we are going to do actually. We are going to prove this by induction, the recurrence relation. Three-term recurrence relation. Was there something like this in Teufel? Three-term recurrence relation. What does this mean? 151. Is this the same? Oh shit, it's the same. Let me try to prove this. I understood the proof from the Doppel-Hart textbook. Alright. If let's say P naught is, that's given, right? P naught is 1, P1 is x plus A1. These are the two. Even in fact in Doppel-Hart they haven't used P1 definition at all. All they've used is P naught. That's the only one polynomial with degree 0 and leading coefficient 1. Let Pk be arbitrary polynomial with leading coefficient 1 with degree k, right? So Pk is x ki power k plus something something something, right? And Pk minus 1, these are computed, P0, P1, Pk minus 2, Pk minus 1. These are orthogonal with degree 1. So Pk minus x times Pk minus 1 belongs to this space of polynomials of up to degree k minus 1. Right? They may not be the leading coefficient 1 polynomial, but it still belongs to this one. And because Pk minus 1, so because this is assumed that these form orthogonal bases, this is equals to some Cj times my projection of Pk minus x Pk minus 1 on Pj times Pj here Pj. Projection on Pj divided by the norm of Pj times Pj. That's like the, yeah, this is a sum. So this is like the sum of Cj Pj. It's like because they are forming the orthonormal basis, sum of Cj and Pj, where Cj is Pk minus x Pk minus 1 Pj. ठीक है, sure. Pj. Now if I want Pk to be orthogonal to all of these previous Pj's, so Pk Pj will turn out to 0. So all C becomes is Cj is minus x Pk minus 1 Pj divided by Pj. This. Right? And how did he prove that all of these are 0 then? This implies that C0 is 0, so up to Ck minus 3 is 0. Why? Why does this imply that? Brother? Here this is equals to, let me write this inner product, that's equals to omega x Pk minus 1 Pj. I can just move the x here. So this is like minus Pk minus 1 x Pj divided by why? Cj, let me write. Cj equals to minus P k minus 1 x Pj divided by Pj. What are we getting here? And to recap, it's pk minus xpk minus 1 equals to sum of cj pj, right? Now what I want to prove is pk is some x pk minus 1 plus some ak times pk minus 1, where ak is x pk minus 1 pk minus 1 upon pk minus 1 pk minus 1. Okay. Let me write ck. Let me write this side. Okay, ck minus 1 is, put j equals to pk minus 1, so it's become j pk minus 1 x pk minus 1 divided by pk minus 1 pk minus 1, right? Was this present here? It's present here. What about ck minus 2? ck minus 2 is minus pk minus 1 x pk minus 2 divided by pk minus 2 pk minus 2. ck minus 3 minus pk minus 1 x pk minus 3 divided by pk minus 2 pk minus 3, sorry, 3, right? I see what they've done. They've used the recurrence relation already. So it's like x pk minus 2, and I wanna use x pk minus 2 from here and bring it to 1 degree smaller and 1 degree larger. So x pk minus 2 will contribute to a pk minus 1, where pk minus 1 stands, and it will contribute to a pk minus xp, so a pk minus 1. Let me write x pk minus 1. What's x pk minus 1? Let me write it here. What is x times pk minus 1? X times pk minus 1 is pk x minus ak pk minus 1, right, minus bk pk minus 2. So if I put x pk minus 1 here, I'm gonna get pk, which is something that why did I not do it here then? Okay, let me write it here, x pk minus 2, right? K equals to k minus 1, so it becomes pk minus 1 pk minus 1, they both are like there, minus ak minus 1 pk minus 2, and pk minus 1 pk minus 2 will cancel out with each other. Pk minus 3 pk minus 1 and pk minus 3 will cancel out with each other. So ck minus 2 only results in this, I think, minus pk minus 1 over pk minus 2 pk minus 2. Yep, perfect. That's what I think the coefficient is. Pk minus 1 pk minus 2 pk minus 2 pk minus 2. Perfect. So it's like you assume it's true and it holds true, therefore it's true. Yeah, the 3-term recurrence relation holds, sure. Cancellation errors can be avoided with clever numerics. So use this 3-term recurrence relation and you can obtain pk. What is pk though? Pk were orthogonal polynomials of up to space k. Yes, pk was orthogonal polynomials. of up to of leading coefficient k, right? Now we have polynomials with this relation. Now I don't understand this. If my orthogonal polynomials with the leading coefficients 1 are going to be defined by this recurrence relation, I want to derive the Chebyshev's polynomials, at least the Chebyshev polynomials recurrence relation. How did you get this? And it should have been of this format, right? Pk is x plus ak times pk minus 1 plus bk times pk minus 2. So in this case bk is sure minus 1, but x plus ak, this is something that I'm not understanding. Why is it 2x? By putting cos alpha equals to x and viewing cos k alpha as a function of x, one is led to the polynomials tk is cos k arc cos x. This is the polynomials cosine k arc cos of x. And minus 1 to 1, and they satisfy this recurrence relation. How? Why? I want to ask this question. Chebyshev notes. Chebyshev polynomial, three term not of that form, right? Not of this form. Chebyshev. When can I ask questions? I should have 100 feedback. When can I ask questions in numerical methods? Example solutions of homeworks. Oh man. All right. So Chebyshev, these are Chebyshev polynomials. It satisfies this recurrence relation with this inner product, with this specified inner product, right? This is the Legendre approximation error in polynomial interpolation. Let f be and let b the n plus 1 distinct nodes. Assume f is continuous or differentiable, then the interpolation error at point xi is at point x is where this belongs to the interval. So the error at any point x is f of x minus the polynomial which interpolates f calculated at x, which was interpolated using x0 to xn points. This is f of f n plus 1th derivative at some g n plus 1 factorial and omega n plus 1 at x, where omega n plus 1 is x minus xi. It's a n plus 1th degree polynomial which has roots at all of the interpolating points. So at interpolating points my error becomes 0 because omega at that omega of the polynomial omega is 0 at that point. Okay, what's the proof of this? It's not in TOEFL hard. At least not in chapter 6. Let me see. On 79. Approximation error. Got it. Found it. Theorem 710, Theorem 710 and Theorem 713. What is Theorem 710? It comes after the divided difference concepts. Theorem 713. This is something about the divided differences things. We'll get to this. Some divided differences things. So error bound requires increasing smoothness with degree n. Can we derive bounds for Ck with k independent of degree n? The bound critically depends on omega plus 1 contain information about the nodes. But not even differentiable. Define the maximum norm. Stone-Weierstrass theorem. of this makes sense to me actually here. All of these slides are. This slide says a missed. Never mind. Let's do the interpolation. Let's approximate fx as 1 plus x square, right? Doing interpolation on equally spaced nodes. I should actually I should look at this. I should see if there is some intuition. The reason I'm not understanding is this because I do not feel this in my body. So I should be able to feel this in my body. Error infinity is f minus pf. What is en star? Oh, the best approximation error with f star is going to be less than what we have. Universal approximation, uniform convergence, that is converges in infinity. However, the sequence of polynomials that converge is not necessarily obtained by interpolation. What they are saying is this is a theorem. This is the theorem they are saying. Can I zoom out a bit? Yeah, this works actually. The theorem that has been posited is En infinity norm of x. This is the one which we get from R f tilde minus f infinite norm, right? Yeah, f tilde minus f infinite norm is equals to En star, that's the best possible, 1 plus lambda n x, which is, now lambda n x is the norm maximum of the sum of Lagrange polynomials. I see. It's the max of Lagrange polynomials. Maximum of the modulus of, in fact, add the mods of Lagrange polynomial. So all there is it decomposes into two components. One is depending on the best approximation. We control the best approximation with the space Pn, sure. We control the Lebesgue constant with the nodes x1, x0 to xn. But there are two important questions to ask about the Lebesgue constant. What are good nodes that keep Lebesgue constant low or even minimize it? In the best case, how does lambda n behave with respect to n tending to infinity? What is n? The number of points. So as I increase the number of points, how does my Lebesgue constant increase? So if xn is n set of n points in a to b, there always exists a continuous function f, so that pf does not converge to f. Okay. They're saying that polynomial interpolation does not allow for approximation in any continuous function. Yeah, that's sure. That's true. Like for example, if there was a kink in a function, if it's not differentiable, then polynomials cannot interpolate it, right? Because polynomials can only interpolate differentiable functions. In fact, yeah. If you're doing an n+1 degree polynomial, then it should then if you're doing an n+1 node interpolation, then whatever our function is should be n+1 times differentiable. It has to be continuously differentiable. Only then our polynomials can converge for n tending to infinity. Okay. That's not, yeah. There exists a, yeah, what is this boy? Why does the Lebesgue constant go to infinity for n going to infinity? Why is this? Why is the Lebesgue constant increasing? That's my question. Lebesgue constant is also the absolute condition number. The thing is, Lebesgue constant increases with n going to infinity, and it depends on the Lagrange polynomials at that Lagrange polynomials of the chosen points of interpolation. Equally spaced nodes in -5 to 5. Interpolants of degree 5 and n. Chebyshev. Using Chebyshev nodes, we are good. Chebyshev nodes are good. The Lebesgue constant for Chebyshev nodes is bounded as this. So 2/pi log n+1 minus c though. 2/pi log n+1 minus c. And now we are going to give an upper bound. 2/pi log n+1 plus 1. Lambda is always less than this. We know that for all interpolation points there exists a continuous function f, so that polynomial interpolation does not converge. Yeah, this is also true for Chebyshev points. However, if f is Lipschitz continuous, then one can show uniform convergence. Yeah. The smoother the function, v times u times and the faster interpolation on Chebyshev nodes converges uniformly. Okay. So this is a general principle. The more easy the function is, the more smoother the function is, the easier it is to. Right. Pointwise evaluation of interpolating polynomials. The interpolating polynomial satisfies the recurrence relation. Okay, this I think is understandable from the proof. All we are doing is just plugging in xi and seeing that it holds for all xi, right? Yeah. Pik is going from I minus k to I. Hermite interpolating polynomial. Hermite. Hermite. Oh, Hermite. Hermite is Indian. Hermite. With a hat. Let me see. Trapetan. What does Trapetan have to say? Any interpolation, iterative methods, it has conjugate gradients, that's it. Eigenvalue system of equations, conditioning instability. So none in terms of interpolation and shit. It has polynomial interpolation, Newton form, polynomial interpolation. What about Dirichlet? Dirichlet has a lot of discussion on polynomial interpolation. None of the Newton method though. Not this Newton basis. Does quaternion have Newton basis? No. It has Hermite interpolation and divided differences. Okay. So yeah, this is it probably. I want to study the divided differences thing. Interpolation and approximation. Maximum of the sum of mod of Lagrangian polynomials. That's the absolute condition number. The polynomial interpolation is linear, therefore Chebyshev nodes slap, bro. Chebyshev nodes are amazing. Yes, we are at the divided differences stuff. Now let's study divided differences from This book's name is Peter and just if one is only interested in interpreting polynomial p at a single position t, then the recursive computation of pt turns out to be the most effective method. नेबीले स्कीम. नबील इस बंदे का नाम है नबील. I know a Nabil. P00, P10, P11. What is this? ये स्कीम कहाँ से आती है भाई? नहीं समझ में आ रहा. I need to understand this divided difference stuff. I know what this means. I know the leading coefficient of the interpolating polynomial is called the divided difference. Fair, but why is this the case? B of n minus 1 is B of... Okay, so... Alright, let me write this. Let me try to show. I can show. I am confident I can show. What am I gonna show? What am I gonna show? What am I gonna show? What am I gonna show is that polynomial, an interpolating polynomial, interpolates f using nodes t0, t1 up to tn is equals to the nth divided difference t0 up to tn, tj omega j sum over j equals to 0 to n. Let's see. Polynomial interpolating f only at point t0. What is this? It's the divided difference. It's whatever the polynomial. What is this? It's going to be t0 f omega 0. What is omega 0? Omega 0 should be just the constant. Just the constant 1 actually. Yeah. So it is just the function value at t0. Yeah, that's the function which interpolates f at t0. That's the not using only one node. If I interpolate a function using only one node, I get this. Let's say I have let's say this is true, that p of n minus 1 is p f t0 up to tn minus 1 is equals to sum of t0 tj f omega j going from 0 to n minus 1, right? Or n minus 2. Using the first n minus 1 nodes, let's say this is true. This holds true. Now what I have to prove is that Pn is Pn minus 1 plus this T naught up to Tn of f omega n of omega n, right? Right? My Pn is obviously by definition this T naught up to Tn f t to the power n plus an minus 1 t to the power n minus 1 plus an minus 2 t to the power n minus 2, right? What is omega n? Omega n is t minus t naught, t minus t1, t minus t2, t minus t n minus 1, right? That's what omega n is. Omega n is of power n. Omega I is of power I, so omega 1. Yeah, so omega n is of power n. So it goes up to n minus 1. This is equals to t to the n, and it goes up to here, t1, t2, up to tn minus 1. This is omega n. If I multiply this with the number t naught up to fn, this becomes t to the n, t naught tn fn plus the same thing, right? And this is this. Substitute this. Yes, and here all of the nodes are of lower powers, tn minus 1, tn minus 2. So let me write this as a polynomial g of order n minus 1, right? So t naught tn f t to the n is t naught tn f omega n minus a polynomial of g minus 1. Let me put this here. So pn is t naught up to tn f of omega n. Two polynomials, let me add them. Let me put this as a q of polynomial of order n minus 1. Right? Where pn was a polynomial that interpolates pn is a polynomial which interpolates my function for these n data points, right? Omega n is also a polynomial which interpolates these functions for these n minus 1 data points though, right? These n minus 1 data points, right? I've got it. So my qn minus 1 is equals to pn minus this t naught up to tn f omega n. Omega n is a polynomial which is something like this: x minus t naught, x minus t1. So it goes up from x0 to xn minus 1, and this polynomial interpolates too. So both of these polynomials interpolate all of points from x0 to xn minus 1. Therefore qn minus 1 has to be pn minus 1, because qn minus 1 interpolates the polynomial for all points up to n minus 1. pn minus 1 was defined this way. So it holds. This is weird actually. It's like this. Let me see. It's t0 f, then t0 t1 f omega 1, then t0 t1 t2 f, then omega 2. It's like, let's say there was no point initially, there was just one point. One point was given to me, just that one point. So my function interpolates, becomes like this. Now another point was added. So now I add a polynomial. Which is 0 at this point, and whatever the value of that point is, this is, so given t naught t1, given 2 points, let's say, I'm having trouble. Given 2 points, it's something like this. Okay, this is understandable. Like every time a new point is added, whenever I evaluated any of these previous points, all of my these terms will cancel to 0. So I only have to show this. I only have to show that this holds, and then on forward. Moving on, I can. So now if this was a polynomial which was interpolating 2 points, let's say t0 and t1. Let me interpolate this polynomial, okay, by using this. Let me interpolate 5x plus 3. First I was given x equals to 0, f equals to 3. This is what I was given. So my interpolating polynomial is that's it, right? At 0 my function value was given as 3. So my polynomial, the polynomial that interpolates that is a straight line that it just goes from 3. Now another point was given to me. F of 1 is equals to 8, let's say. So now I calculate this. How do I calculate this though? This comes out as 5. So my new addition of the polynomial is this times omega, and omega is x minus 0, so it's 5x plus 3. That works, bro. I want to do it for some higher polynomial actually. Why does this, I don't have a feeling for it though. This is like just a straight line, just a polynomial of order 0 which goes through that. Then whenever you add a new polynomial, it's a polynomial of order 1 greater than that, which is 0 on all of those points, just the new point which is being supported. Then whenever you add a new point, the polynomial is a degree greater than that, so that it's 0 for all of those previous points. It's 0 for all of those previous points. It's just going to add a new number and it's just going to add a new number such that that new point that you're evaluating on, it has the same value there. Divided difference. Why is it called divided difference, bro? The divided difference satisfies the following properties: t0 to tn, p is 0 for all p in pn minus 1. Okay, for multiple nodes it's okay. The following recurrence holds. Why is this true? T0 T1 is remove T1, put it there. It's 2. Remove T1 is T0 1. See, this becomes f of T0 T1 is equals to f of T0 minus f of T1. F of T0 is T1 removed, so minus T1 and T0. F of T0 is 1 minus 2 divided by T0 is 0 minus 1, so it's like 1. I know how to calculate it, but I do not get the feeling for it still. I don't feel this Newton's basis. Approximation error. Okay, approximation error is given in the trigonometric interpolation. Let me see. Let me open the slides again. What else is left? About divided differences. I understand that thing. I'll be able to do the problems that they ask. I don't feel it, to be honest. Hermite interpolation. This is the Hermite interpolation. This is just plug and chug. When xi will be equal to xj, when x will be equal to xj, this term goes to 0. This will be xi minus xj should be 0, right? Should be 0, right? I don't understand this. This interpolates at xi, right? The left hand side interpolates at xi. If I put x equals to xi, left hand side is 0. What about the right hand side? X equals to xi, this is 0. Xj minus xi, p of, but it does not interpolate at xi. So it's like, even in Teufelsdorf, the definition is the same. At t equals to tj, at t is equals to tj, this function, this polynomial is some non-zero value, this is some 0 value. What about the Aitken lemma? Right. At x0, this is 0. No, not, I should not say 0 then. For x equals to xi, this is whatever the interpolant is at xi. This goes to 0. X equals to xi, these cancels. And this will not be f of xi because it's not interpolating at f of xi, right? It's like same here. Aitken lemma. Hermite interpolation recurrence relation notes. This I understand, this I can prove. This I understand, divided difference I understand. Why do the divided difference follow this property? Just assume that they do. I don't care about that. Trigonometric interpolation. Interpolation means approximating function values in the interior of a domain where the known samples of a function at a set of interpolation amounts to solving a linear system of equations. Not Chebyshev notes. Higher dimensions. Okay. 13 is done. 20 slide is non-linear. This is non-linear equations. Okay.